study the behavior of a prism, lens and mirror. What happens when plane wavefront is incident on the prism like this. So this is a plane wavefront which is incident on the prism. Here this represents a plane wavefront and these are the incident rays. We know that incident rays are perpendicular to the wavefront. What happens when this incident wavefront, plane incident wavefront is incident on the prism? What happens to the emergent wavefront or what happens to the refracted wavefront? We have to draw the refracted wavefront. See here, if you consider this part of the wavefront or this ray passes through small thickness, here thickness is less. Okay, so this part of the wavefront or this ray passes through average thickness. Here this part of the wavefront or the ray passes through maximum thickness, isn't it? Hence the upper part of the wavefront, okay, the upper part of the wavefront travels through minimum thickness and hence it travels faster. And the lower part of the wavefront passes through maximum thickness and hence it gets slowed down. Okay, so the lower part of the wavefront passes through the maximum thickness and hence gets slowed down. So how will you draw the refracted wavefront? Here this part of the wavefront travels faster, isn't it? So that part wavefront reaches here. Here this part of the wavefront it travels through average distance, average thickness. Therefore it cannot travel that much distance, let it covers distance like this. Here this part of the wavefront here passes through maximum thickness and therefore it gets slowed down, let that part of the wavefront reaches here. And if we join, this is the refracted wavefront. This represents the refracted wavefront. And how will you draw the rays? Rays are always perpendicular to the wavefront. So here we can draw the rays like this. These are the rays. Rays are always perpendicular to the wavefront and this represents the rays. These represent refracted rays and this represents the refracted wavefront. The refracted wavefront, emergent wavefront is slightly oblique. Okay children. Now second one, what happens when a plane incident wavefront is incident on a convex lens? Okay, plane wavefront is incident on a convex lens. Here the upper part of the wavefront passes through minimum thickness. So here the upper part of the wavefront passes through minimum distance, therefore it can travel more. Here the middle portion of the wavefront passes through maximum thickness. Here the middle part of the wavefront travels through maximum thickness and hence it gets slowed down. Here the bottom part of the wavefront also travels through minimum thickness, therefore it can travel more. Okay children, so here this part of the wavefront can travel more. Here this part of the wavefront cannot travel as such. Here let is the distance or it covers a distance like this. Here the bottom part of the wavefront can travel more distance like this. So if we join the points, we will get a spherical type wavefront. Okay children, when a plane wavefront is incident on the convex lens, what happens to the refracted wavefront? This is the refracted wavefront. Refracted wavefront is spherical. When a plane wavefront is incident on the convex lens, the refracted wavefront, emergent wavefront is a spherical wavefront. Now, how will you draw the rays? We know that rays are always perpendicular to the wavefront, isn't it? So, these are the rays. These are the rays and it meet at a point which is called a focus. Because here wavefront, this represents the incident wavefront, means here where is the object? Object is at infinity, isn't it? Wavefront, incident plane wavefront means here the object is at infinity. And object at infinity means where is the image formed? Image is formed at the focus. So what is the shape of the refracted wavefront? It will be a spherical wavefront. Now we can discuss what happens when a plane wavefront is incident on a concave mirror. This represents incident plane wavefront. What happens when it is incident on a concave mirror? Okay, so here this represents the incident plane wavefront and these are the incident rays. If you see, the center portion of the incident wavefront has to travel longer distance before gets reflected. Okay, so this portion of the wavefront has to travel longer distance before get reflected. Therefore, the center portion of the wavefront of the reflected wavefront is closer to the mirror. Center portion of the reflected wavefront is closer to the mirror compared to others too. So, here this region has to travel not much distance. So, therefore, it gets reflected and reaches here. Here, similar to the bottom region, bottom portion of the wavefront also travel to not much greater distance. Okay, so therefore, after reflection it reaches here. But center portion has to travel longer distance before it gets reflected, and hence the reflected wavefront position is slightly closer to the mirror. Okay, children. So, if you join the points, you will get a reflected wavefront. This represents the reflected wavefront. Clear, children? So, this is the reflected wavefront. Now, how will you draw the rays? Rays are always perpendicular to the reflected wavefront. So, these are the reflected rays perpendicular to the wavefront, and they meet at the point which is called a focus, because here object is at infinity. Incident plane wavefront represents object at infinity. Where is the image formed? Image is formed at the focus. Clear, children? So, this is the behavior of a prism, lens and mirror when plane wavefront is incident. In the case of prism, the refracted wavefront is slightly oblique. In the case of convex lens, when the plane wavefront is incident, it becomes spherical wavefront. And here in the case of concave mirror also, when plane wavefront is incident, reflected wavefront is spherical in nature. Dear children, have you seen colors on soap bubbles, colors on oil films, beautiful colors in butterfly wings and peacock tail? All these are due to a very important phenomenon called interference of light. We are going to study about a very important phenomenon of light, that is interference of light. When two light waves of same frequency, amplitude, velocity, wavelength having same phase or constant phase difference traveling in the same direction superimpose each other, the intensity get redistributed, become maximum at some points and minimum at some points. This phenomenon is called the interference of light. When two light waves having what are the properties? Same frequency, amplitude, velocity, wavelength, having same phase, constant phase difference, same phase or constant phase difference, and the two waves must be traveling the same direction. When they superimpose means when they combine, superpose each other, the intensity get redistributed. In some regions intensity will be maximum, and in some other region intensity will be minimum, or alternate bright and dark bands are formed, and this phenomenon is called the interference of light. The two sources of light which continuously emit light waves of same frequency, amplitude with zero or constant phase difference are called coherent source. So, sources which produce light of same frequency, amplitude, wavelength, velocity, zero or constant phase difference, such sources are called coherent light sources. Okay, so two sources which do not emit light with constant phase difference, they are called incoherent source. Okay, so only coherent source can produce interference pattern. Coherent source means two light sources which produce light of same frequency, velocity, wavelength, constant phase or zero phase difference. Such sources are called coherent source, and only coherent source can produce interference pattern. Now, what is the example for coherent source? Two independent sources of light cannot be coherent. That is, two bulbs of 60 watt. Okay, two separate bulbs of 60 watt each, they cannot act as coherent source, because they may produce light of same frequency, velocity, wavelength, etc., but the phase or phase difference may not be same. Okay, so two separate bulbs of same company, same manufacturing date, everything same, they produce light of same frequency, velocity, wavelength, etc., but what will be different? Phase or phase difference will be different. Phase or phase difference represents the intrinsic property. Okay, they will not be same for two bulbs, and hence two separate bulbs, two independent light sources cannot be coherent. So, how can we construct a coherent source? So, example of coherent source is, this is a slit, this is a source, yes, in front of it there is a small slit placed to make the light in a straight line like a beam. Okay, so this is original source and here a small slit is placed in front of it so that light is move in the form of beam. Okay, we can collimate the light. Now two slits, very small slits are placed in front of the original slit. So here light coming out of these slits, slits means small opening, these slits act as coherent because these light waves are produced from the original source, okay, from the same source. So they are equidistant, these two slits are equidistant from the original source and hence they produce light of same frequency, velocity, wavelength, and since they are formed from the same source, phase or phase difference will be same. Okay, so two slits S1 and S2 placed in front of source S act as coherent. Whatever phase changes occur in S1, the same phase change occur in S2. If there is any change in S1, same phase change occur in S2 because they are formed from the same source. Okay, and hence the phase difference between S1 and S2 remains same. So they act as the coherent source. Okay, so this is the method of constructing coherent source. So two separate bulbs cannot act as coherent, and what is the example for coherent? Two slits, two openings placed in front of the original source, they act as coherent because they produce light of same frequency, velocity, wavelength, etc. And since they are produced from the same source, phase or phase difference will be same. Okay. In the figure we can see double slits placed in front of the single slit. The double slits act as coherent source and here we can see alternate bright and dark bands. That is the clear interference pattern. So we have studied what is interference and we have seen the interference pattern. What is the interference pattern? Alternate bright and dark bands, isn't it? Now we can derive the condition for bright band or otherwise called constructive interference and dark band otherwise called destructive interference. Okay, so now we can derive the condition for bright band and dark band. Now first case, consider the original source S and consider two slits placed in front of the original source and these two slits act as the coherent source. Okay, now consider a screen placed at some distance from the coherent source and P be a point at the center point. Now waves are travelling from S1 to P, wave is travelling from S2 to P and at the point these two waves superimpose. Okay, as a result interference pattern is formed. It may be a bright band or dark band. Okay, so first P be a point at the center. So what is the path of light travelled by the light waves from S1 to P? What is the distance travelled by light from S1 to P? That is S1P. What is the distance travelled by light from S2 to P? That is S2P. So these are the two slits. So light travels from S1 to P and light travels from S2 to P. Since P is the center point, these two distances are equal. So the path difference, what is the path difference at the point P? At P we can write path difference. Path difference, that is S2P minus S1P. Okay, S2P minus S1P equal to 0 because both the distances are equal, no? S1P and S2P are equal. So path difference at the point P, path difference is equal to 0. For example, if let S1P equal to, example we can take, let S1P equal to some phi lambda. S2P also will be equal to phi lambda. Okay, phi waves travel from S1 to P. Similarly, phi waves travel from S2 to P. So what is the path travelled by light from S1 to P? Phi lambda. S2 to P, that is also phi lambda. Let. Okay, so what is the path difference here? Both are equal, so path difference is equal to 0. Since P is at the midpoint, S1P and S2P are equal, path difference is equal to 0. Now what is phase difference? Phase difference means that is related to angle. The relation between path difference and phase difference is equal to 2 pi by lambda into path difference. This is the relation between path difference and phase difference. Okay. So the relation between phase difference and path difference is equal to 2 pi by lambda into path difference. By heart the formula. This is the important relation between phase difference and path difference. So here in this case, what is the phase difference? Phase difference is usually represented by the letter phi. So here phase difference is equal to, since path difference is 0, phase difference is also equal to 0. Clear? Now the first wave from the source S1 can be written as, the wave from S1 can be written as Y1 equal to A cos omega t. This is a wave equation. Any wave can be represented as Y. Y represents the displacement, A cos omega t. Okay, any wave can be written as Y equal to A cos omega t, where Y is called displacement, A is called amplitude, omega t is called phase. You have studied this in the last year class, 11th standard waves chapter. So displacement of a wave is given by Y equal to A cos omega t. Here displacement from the first light source can be written as Y1 equal to A cos omega t. Wave from the second light source is also A cos omega t. Okay, so these represents the displacement from each light source. So displacement produced by S1 is Y1 equal to A cos omega t. Displacement produced by S2 is Y2 equal to A cos omega t. Okay, both have same amplitude because they are coherent. Both have the same phase, omega t. Both have same phase. Okay, so if these two waves, so these are the waves from the two coherent source, Y1 and Y2. If they superimpose at the point P, we are discussing about the point P. At the point P they superimposed. That means the superimposed wave can be written as superimposed wave. Superimposed wave is, how will you write, Y equal to Y1 plus Y2. Okay, so it is equal to Y1 is A cos omega t, Y2 is equal to A cos omega t. So if you take the sum, 2A cos omega t. So the resultant wave is Y equal to 2A cos omega t. Okay children, so we have seen the two waves. First one is A cos omega t, second wave is also A cos omega t, since they have same phase. Okay, phase difference is equal to 0. Here phase is omega t, here also phase omega t. When they superimpose to form, the resultant wave is 2A cos omega t. Clear? Now the amplitude of the each wave is A. A represents the amplitude. Both have the same amplitude. So amplitude of each wave is A. What is its intensity? We have intensity is equal to amplitude square. Intensity is equal to amplitude square. So the amplitude of each wave is A. So intensity is equal to, what is the intensity of each wave? A square, which can be written as I0. So intensity of each wave is I0 equal to A square. Similarly, what is the amplitude of the resultant wave? 2A. Okay, A cos omega t and A cos omega t combines to form 2A cos omega t. So amplitude of the resultant wave is 2A. So what is its intensity? Its intensity is 2A square, 2A the whole square. That is equal to 4A square. That is equal to 4I0, because A square we have taken it as I0, isn't it? A square equal to I0. So the intensity of the resultant wave is 4I0. That means intensity is maximum where a bright band is formed. Okay, so condition for bright band 4I0 is, what is the condition? Path difference is equal to 0 or phase difference is equal to 0. So if path difference is equal to 0 or phase difference is equal to 0, intensity will be maximum, which is 4I0, and in that case a bright band is formed. Okay. Now we can discuss another case, condition for bright band. So first condition is path difference 0, phase difference equal to 0. Now again we can consider the same example. Consider two slits S1 and S2, coherent source placed in front of the parent source. Okay, parent light source. Here is a screen. This represents a center point. Now we can consider another point P. Okay, P, it is not at the center point, it is at some distance from the center. P be another point which is some distance from the center. So we have to find another condition for bright band. For that, light wave travel from S1 to P. Light wave is travel from S2 to P. Okay, light waves travel from S1 to P. So what is the path travelled by light from S1 to P? That is S1P. What is the path length of distance covered by light from S2 to P? That is equal to S2P. So what is the path difference at P? Now P is not at the center, it is at here. At P, what is the path difference? Path difference is equal to S2P minus S1P. They are not equal, no? S2P and S1P are not equal. Okay, for example, we can assume S1p equal to some 7 lambda. S2p is equal to some 8 lambda. 8 lambda means 7 waves are travelling from S1 to P. 8 waves are travelling from S2 to P. Clear children? From S1 to P, 7 waves, 7 lambda, 7 waves are travelling. S2 to P, how many waves are travelling? Let 8 waves are travelling. Here just we have assumed S1p equal to 7 lambda, S2p equal to 8 lambda. Clear? Now, what is the path difference here? Here, path difference is equal to, using this example, we can write path difference equal to S2p minus S1p equal to 1 lambda. 8 lambda minus 1 lambda equal to, 8 lambda equal, minus 7 lambda equal to 1 lambda. Again, what is the phase difference here? Phase difference is equal to 2 pi by lambda into path difference, no? So, 2 pi by lambda into 1 lambda. So, equal to 2 pi. So, if we have taken S1p equal to 7 lambda, S2p equal to 8 lambda, path difference become 1 lambda, phase difference becomes 2 pi. Clear children? Again, we can assume first wave y1 equal to A cos omega t, that is the displacement produced by S1. Displacement produced by S2 is y equal to A. Amplitude should be same, cos omega t. Here what is the phase difference between these two? The phase difference between these two is equal to 2 pi, no? So here we can take cos omega t plus 2 pi. Now the phase difference between them becomes 2 pi. Here it is omega t, here it is omega t plus 2 pi. So what is the phase difference between them? 2 pi. Okay. So first wave y1 equal to A cos omega t, second wave can be written as y2 equal to A cos omega t plus 2 pi. Now the superimposed wave can be written as, superimposed wave is y equal to y1 plus y2. Here we can take A cos omega t plus 2 pi. What is cos omega t plus 2 pi? Cos theta plus 2 pi. Cos theta plus 2 pi is cos theta, isn't it? Cos theta plus 2 pi means 360 degree. Theta plus 360 degrees, same value cos theta. So here also A cos omega t plus 2 pi is what? That is also A cos omega t. Clear children? A cos omega t plus 2 pi is same cos omega t. So y2 is no change, A cos omega t. So what is the superimposed wave? Y equal to y1 plus y2. It is equal to, if we substitute, it becomes 2A cos omega t. Okay, superimposed wave y equal to 2A cos omega t, similar to the first case. What is the intensity of the superimposed wave? Intensity of the superimposed wave is amplitude square. What is the superimposed wave amplitude? 2A, no? So same as the before, 2A the whole square, that is equal to 4I0. Okay, 2A the whole square, that is 4A square. A square is equal to intensity of the each wave. Okay children, so here also 4I0. If intensity is 4I0, which band is formed there? Bright band is formed. So what is the another condition for bright band? Path difference is equal to 1 lambda. Okay, phase difference is equal to 2 pi. If path difference is equal to 2 lambda, what will be the change? For example, here S1p equal to 7 lambda, S2p equal to 9 lambda. Just if you take 7 lambda, 7 waves are travelling from S1 to P. 9 waves are travelling from S2 to P. So what is the path difference then? 2 lambda. What will be the phase difference? 2 pi by lambda into 2 lambda. So it becomes 4 pi. Clear children? Here A cos omega t plus 4 pi, theta plus 4 pi, cos theta plus 4 pi is also cos omega t. There also which band is formed? Bright band is formed. Clear? Again, if path difference is equal to 3 lambda, here phase difference becomes 6 pi. Correct, 6 pi. There also intensity is 4I0. So if path difference is 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, etc., and phase difference becomes 2 pi, 4 pi, 6 pi, 8 pi, etc., which type of band is formed? Bright band is formed. Okay, here in the first case we have discussed path difference is equal to 0 or phase difference is equal to 0. There also which band is formed? Bright band is formed. Okay children, so generally we can write Condition for bright band or constructive interference is path difference is equal to 0, then 1 lambda, then 2 lambda, 3 lambda, 4 lambda, etc. We can write n lambda. Okay, 0, 1 lambda, 2 lambda, 3 lambda, etc. or n lambda, we will get a bright band. So, condition for bright band is path difference is equal to 0, 1 lambda, 2 lambda, 3 lambda, etc. or n lambda. Similarly, phase difference we can write 0, now 2 pi, then 4 pi, then 6 pi, etc. we can write 2n pi. Put n equal to 0, we will get 0. Put n equal to 1, 2 pi, n equal to 2, 4 pi, n equal to 3, 6 pi, etc. So, phase difference is 0, 2 pi, 4 pi, 6 pi, etc. 2n pi. There also which band is formed? Bright band is formed. So, what are the values of n? 0, 1, 2, 3, etc. So, the condition for bright band is path difference equal to n lambda and phase difference is equal to 2n pi. Okay, children? Now, we can derive the condition for dark band. Here also we can consider two slits S1 and S2. S represents the original source and consider a screen. Here this represents sender and consider another point P. Okay, another point. Here what is the path travelled by light from S1 to P? That is S1P. Path travelled by light from S2 to P, that is S2P. So, what is the path difference? Here also S2P minus S1P. Let S1P is equal to some 5 lambda and S2P is equal to 5.5 lambda. Okay, children. So, 5 waves are travelling from S1 to P. 5.5 waves are travelling from S2 to P. So, S1P 5 lambda, S2P 5.5 lambda. So, here what is the path difference? Using the example, path difference is equal to 5.5 lambda minus 5 lambda, that is equal to 0.5 lambda. According to the example, path difference is equal to 0.5 lambda. So, now what is the phase difference? Phase difference is equal to 2 pi by lambda into 0.5 lambda. No, phase difference is equal to 2 pi by lambda into path difference. So, 2 pi by lambda into 0.5 lambda, that is equal to pi. So, here according to the example, path difference is 0.5 lambda and phase difference is equal to pi. Now, the first wave can be written as y1 equal to a cos omega t, no change. Second wave can be written as a cos omega t plus pi, because the phase difference between the two waves is equal to pi. We have taken phase difference as pi. So, the first wave can be written as y1 equal to a cos omega t and second wave can be written as a cos omega t plus pi. What is this a cos omega t plus pi? Cos omega t plus pi, cos theta plus pi, that is equal to minus cos theta. Okay, cos theta plus pi is minus cos theta. So, here it becomes minus a cos omega t, theta plus pi. Okay. Here it becomes cos omega t plus pi, that is equal to minus a cos omega t. So, what is the resultant wave? Resultant wave is y equal to y1 plus y2. Okay, children. So, y1 is a cos omega t, y2 is equal to minus a cos omega t. So, what is the resultant? Resultant is equal to 0. So, resultant 0 means which type of band is formed there? A dark band is formed. This is a dark band. So, intensity is resultant wave is 0 means what is the intensity? Intensity is also 0. Intensity is equal to 0, that means a dark band is formed. Clear, children? So, here if you take another example, if it is 5 lambda, here it becomes 6.5 lambda. Let 5 lambda and 6.5 lambda. So, what will be the path difference? Here it becomes 1.5 lambda. Okay. Here what is the phase difference? 2 pi by lambda into 1.5 lambda, it becomes 3 pi. Okay, children. So, there also omega t plus 3 pi, that is also minus a cos omega t. Clear, children? So, here if you take 0.5 lambda, the difference is 0.5 lambda. If path difference is 1.5 lambda, if path difference is 2.5 lambda, 3.5 lambda, etc. There what type of band is formed? Their intensity will be 0 and the dark band is formed. Clear children? So the condition for dark band or destructive interference is, what are the values of path difference? As discussed, path difference is 0.5 lambda, 1.5 lambda, 2.5 lambda, etc. Isn't it children? So path difference is 0.5 lambda, or we can take 1.5 lambda or 2.5 lambda, etc. Or you can write 2n plus 1 into lambda by 2. We can check. Put n equal to 0, it becomes lambda by 2, that is 0.5 lambda. Put n equal to 1, 3 lambda by 2, that is 1.5 lambda. If put n equal to 2, 5 lambda by 2, that is 2.5 lambda. So this is the final value. So path difference is 0.5 lambda, 1.5 lambda, 2.5 lambda, etc. 2n plus 1 into lambda by 2, general condition. Similarly, what are the values of phase difference? Pi, then 3 pi, then 5 pi, 7 pi, etc. Pi, 3 pi, 5 pi, 7 pi, etc. Or you can write 2n plus 1 into pi. That also we can check. Put n equal to 0, that is pi. N equal to 1, that is 3 pi. N equal to 2, that is 5 pi. Okay children. So the general condition for dark band is, path difference is 2n plus 1 into lambda by 2 and phase difference is 2n plus 1 into pi. Okay children. So these are the conditions for dark band and bright band. So if the condition for bright band is satisfied, their bright band will be formed, and if the conditions for dark band is satisfied, at the position dark band is formed. Okay. So in the previous section we have discussed the condition for bright band and dark band. Bright band otherwise called bright fringe, dark band otherwise called dark fringe. So the condition can be derived in another method. So that method we are discussing now. Okay, using trigonometric function easily we can derive the condition for bright fringe and dark fringe. We have the first wave, the displacement of the first light wave can be written as a cos omega t, and the displacement of the second light wave can be written as a cos omega t plus phi. Here we have assumed phi be the phase difference between the two light waves. Amplitude of each wave is a. So what is its intensity? Amplitude square, I0 equal to a square. Clear children? Now these two waves superimposed. So what will be the resultant displacement? Resultant displacement is y equal to y1 plus y2. That is y equal to y1 is a cos omega t plus y2 is a cos omega t plus phi. We can take a common. We can write a into cos omega t plus cos omega t plus phi. Okay, so that is displacement y. Now we have the formula trigonometric function. We have the trigonometric function, trigonometric identity cos A plus cos B. This is of the form cos A plus cos B. No, cos A plus cos B is 2 cos A plus B by 2 into cos A minus B divided by 2. Cos A plus cos B is 2 cos A plus B by 2 into cos A minus B by 2. Okay, so this is the trigonometric identity. Using this identity, we can write y equals here 2a plus b by 2. Let this is omega t plus phi is a, omega t is b. Okay, this is a, here this is b. So cos a plus b by 2, a plus b by 2 means omega t plus phi plus omega t divided by 2, that is cos 2 omega t plus phi by 2 into cos a minus b by 2, that is omega t plus phi minus omega t by 2, that is cos phi by 2. Clear children? So 2a cos 2 omega t plus phi the whole by 2 into cos phi by 2. This can be rearranged and write 2a cos phi by 2 into cos 2 omega t plus phi divided by 2 can be written as omega t plus phi by 2. Okay children? So displacement y can be written as 2a into cos phi by 2 into cos omega t plus phi by 2. This we have taken cos phi by 2 in the beginning because this is a constant. This does not depend on time. Okay, so displacement of the resultant wave is y equals 2a cos phi by 2 into cos omega t plus phi by 2, where phi is the phase difference. Now, what is the amplitude of the resultant wave? Amplitude of resultant wave. Amplitude of the resultant wave is here 2a cos phi by 2 represents the amplitude. It's a constant, it does not depends on time, no? So, 2a cos phi by 2 represents the amplitude. So, amplitude is 2a cos phi by 2. Now, what is the intensity? Intensity of the resultant wave is I equal to amplitude square. We know intensity is equal to amplitude square. That is 4a square cos square phi by 2. Okay, so amplitude is 2a cos phi by 2. Intensity of the resultant wave is amplitude square. That is 4a square cos square phi by 2. Okay. That intensity can also be written as 4a square is I0. A square represents intensity of the each wave, which is I0. So, 4I0 cos square phi by 2. So, the intensity of the resultant wave is 4I0 cos square phi by 2. Okay, let phi equal to, if phi equal to 0, then 2 pi, then 4 pi, etc. If phi equal to 0, or phi equal to 0, what is the intensity? It becomes cos 0, phi becomes 0 means cos 0 is 1. So, intensity is 4I0. If phi equal to 2 pi, 2 to cancel, cos pi, which is minus 1 square, so it is 1. So, intensity again 4I0. If phi is equal to 4 pi, phi becomes 4 pi. Again here after simplification it gets 2 cos square 2 pi. So, it is 1. So, again 4I0. So, if phi phase difference phi equal to 0, 2 pi, 4 pi, 6 pi, etc. or 2n pi, which band is formed there? There a bright band is formed or a bright fringe is formed. Bright band or bright fringe or constructive interference. So, condition for bright band is path phase difference phi. Phi represents the phase difference. Phi is the phase difference. So, phase difference phi equals 0, 2 pi, 4 pi, etc. to n pi. Similarly, if phi equals pi, 3 pi, 5 pi, etc. If phi equal to pi, 3 pi, 5 pi, etc. If phi equal to pi, put phi equal to pi, cos pi by 2, cos square pi by 2, pi by 2, cos pi by 2 is 0. So, it becomes 0. If phi equal to 3 pi, cos 3 pi by 2 again 0. So, intensity is 0. Okay. So, if phase difference phi becomes pi, 3 pi, 5 pi, etc. or 2n plus 1 into pi. Okay, 2n plus 1 into pi. If phi equal to pi means cos pi by 2, that is 0. So, intensity will be 0. Okay, so if phase difference is 2n pi, that is a condition for bright fringe where intensity is 4I0. If phase difference phi equal to 2n plus 1 into pi, that is a condition for dark fringe and their intensity is 0. Already we have discussed this in the previous section. Okay, so either we can use that method to derive the condition for bright fringe and dark fringe, or using this easy trigonometric functions, using this trigonometric method we can derive the condition for bright fringe or dark fringe.